Hello everyone, welcome back to the series on programming robot mechanics. And from this video onwards, 3 or 4 videos, for the next 3 or 4 videos, we are going to work on solving the inverse kinematics of the robot. Now, why 3 or 4 videos? Because inverse kinematics is a very broad area of sub study. We will need to code different components of the inverse kinematics to make it work. Well, I did study about inverse kinematics and there are various ways to solve it. Once the most used way is the optimization one, where we use some deterministic optimization techniques to solve the inverse kinematics. There are also some methods like genetic algorithms, which I thought of using and they sounded pretty interesting to use, but we're not going to use them for the time being. It would be really good to code a solution using genetic algorithm or GA, but let's not do it for now. Let's just focus on a simple optimization route. Right. So in this video, what we are going to do is to code the first part of that inverse kinematics. But before doing anything, we are going to separate, or we can say modularize a bit over here. So for that, what we're going to do, we are going to define some folders and put every file in its related folder. We are going to make 2 folders. First is going to be robot, and we are going to put link and the robot file inside the robot. Okay, that's done. And then we are going to define a new folder. We'll name it tools, and we will put transformations and visualize inside tools, because these are tools. And the inverse kinematics that we are going to define is going to be something in tools and somewhat in robot as well. So let's see what we get. Now part 9 is saying this, and whenever we put something in a folder, we always need to generate an underscore init file. That is important. Otherwise, Python does not recognize that the module that we have is kind of like a package. Oh, so it's read it. Just remove it. Okay, so we'll do that. We will rename it and we will name it file. Okay, similarly for the tools as well. Okay, so we have the libraries now. A lot of things are not going to work, like this is not going to work. Now we are going to need robot.robot import robot, because the robot file, the robot class is present inside robot, which is present inside the robot file. Similarly, the tests are not going to work. So from link, we don't need to do that. We need to do from robot.link, import link. Similarly, for test robot, we need to do from robot.robot import and robot.link. Well, Visual Studio is automatically directing us to do the required changes, like wherever it feels something is wrong. And right. So now the unit tests should work. Let's run them. First, we'll go to the folder. And then we're going to activate the particular environment. Then we're going to go to part 9, then test. And then we're going to run Python test.py. Now it says from link. Okay. Okay. So, all right. See. Okay. So it does not, but the error doesn't seem to be coming from that. Robot.robot import robot line 6. And in that, okay, I think we can do this then. And tools. Yeah, so it's now working. Right. We just needed to add robot, because now robot is being treated as a module because of this init.py, and tools is also treated as an init.py. One thing to note is that these two files, the robot file and the visualize file are present in 2 different folders, but using this tools.visualize, we are able to see or use the file that are present over there. I think we can do this for here as well if we want, but I don't know. We'll try it later, or we can just try it, right? All we need to do is just remove this and let's see if this works. Just an experiment. Okay, doesn't work. No module name to. Okay, it doesn't work. So we'll just let it be. All right. All right. Okay. So now for the real part of the video, now we have done some rearrangement of the stuff over here. And now we are going to work on an optimizer that we're going to use. And that optimizer is Newton-Raphson method. Well, yeah, that is the optimizer that we're going to use. Now, what Newton method optimizer does, we're just going to call it Newton method. Optimizer seems a little big name. So what Newton method does, we'll be seeing in this GIF. This is a Wikipedia site of Newton's method. First of all, we have an initial value x1. We calculate a tangent and we get the x-axis where it intersects it. And then we again draw the tangent and get where the x value intersects. Similarly for x, and we keep on doing this until we converge to a solution where f of x is equal to 0. Now this method is really powerful. Well, it converges really fast. So this is a method that we're going to use for our inverse kinematics. Right now, currently the formulation is going to be a simple scalar function. That is, we give a single scalar input, we get a single scalar output. But in the future or in the next 1 or 2 videos, we are going to extend this Newton method to vector values or matrix values as well, because the function that we are going to optimize, like f of x equals 0, is going to take an input, the joint angles. Right. I think something like that, like the input and output space are going to be joint angles and the XYZ coordinates. So these are not a single scalar value, but a vector of values. That's why we need to extend it when we go forward in the next thing. Okay, now what the formula that we are simply going to code this formula, like while solving the iteration, every n+1, in order to get the next step of x, we need to apply this formula, xn minus f of xn divided by f dash of xn. Now f dash of xn stands for derivative of xn, and we need to code the derivative as well. For that, we are going to use the definition of derivative. Since this is also Wikipedia website, we are going to use the simple definition of derivative, like limit h tends to 0, f of a plus h minus f of a divided by h. So h, we are going to take a really small value, like 10 to the minus 9 or something like that, and then we are going to calculate the value. This is going to be approximately equal to the derivative, not exactly, but yeah, approximate values for us would definitely work. Right, so let's do this then. One other thing that we could do, which I am thinking about, when we calculate this limit h tends to 0, no, I think, yeah, it would work. Nothing. It would work. So first of all, we will try and code the derivative. Right, now we are going to do this in the tools. And in the tools, we are going to define optimizers. .py. Right, so this is an optimizer module that we have. Let's check some documentation. Optimizer. And we are going to import numpy as np because that is required. This you are going to do this and that. Okay. All right, now we are going to define a function by the name of derivative, and we are going to take a function f and a value x, at which point we require the derivative to be calculated. Let's add some documentation. But before why we are adding this underscore over here now, and derivative is typically not going to be useful in all the code base that we have. Or the only way, is the spelling correct? Derivative, yeah, derivative. Okay. Now the only place where derivative is going to be used is in the optimizers module. If in the future we use it, we will remove this underscore. This underscore only denotes that the derivative function is only applicable inside this file only. That's what it does. So let's write some documentation for it first. All right, so we have this now. So we're going to use the simple formula. What we can do, we can adjust an epsilon that can be adjustable to the value that we want. We're going to put this 10 raised to power minus 10 but this is adjustable by the user that wants to adjust this according to their needs, like the precision that they want. So this is going to be an optional value, and yeah, adjustable position, adjustable precision. Okay, now we are going to define two x's. X1 is going to be x plus epsilon, or right, okay, let's not name it x1, let's name it an x underscore, just any temporary name that would do. So we are going to put the epsilon, right? And now we are going to calculate the limit, or simply value, because that is the thing that we are going to return. Okay, we are going to take f of x underscore minus f of x, and we are going to divide this whole thing by epsilon, and then we're going to return the value. This is going to be really simple. Yeah, I think it will be really simple. So let's just first test it. Okay, one more thing that we can do is we will write the unit tests of everything all at once. So that will be easy. In this video, we are only going to write the Newton optimizer. So we are going to write the unit tests of them as well, along with the complete code. So now let's start writing the Newton method. Okay, now, yeah, let's define some epsilon for this as well. That should be, yeah, similar to that 1e minus 10. Now this epsilon is actually the value. Oh, this is optional. This epsilon is actually the value that we wanted to converge to. Like, we will check the error whenever this error comes close to this epsilon, like less than epsilon, then we are going to return the value. Well, there are many ways that we can define this Newton method. We can make it as flexible as we want. For instance, there are two ways that it will converge. Either we have the number of iterations that we wanted to converge till, or we can have this epsilon convergence, or we can have both of them. But for now, let's focus on simply the epsilon convergence. Like, we will calculate the difference and see if the values are close enough. And if they are close enough, then we will terminate the optimization routine. And then we will also log some of the results as well. Now, pref value, we will be going to take it x init plus 1. Now, why I'm doing this? Okay, let's take it like this, 2 times epsilon. This way, if whenever the user changes the x init values and epsilon values, that way the error that we will calculate, like while starting this loop, let's just first do that and then I'll show why. Okay, so this is how we're going to do it. Now we are going to compare the previous value and the current value with epsilon, like their difference and absolute difference. We are going to take the initial value of previous value as x init plus 2 times epsilon. We are going to do this in order so that if the x init and epsilon are changed by any users, this way the optimization routine will run in any way possible. We are just not hard coding any values, so the optimization routine just works as it is. Right, now we are going to apply the value. Okay, first of all, we are going to assign previous value to value because that's required. And then we are going to take in value minus f of x. Now this is going to be f of x divided by the derivative of f of x. Or we can say, right, I think we can do it something like this. We can calculate the derivative first and then call in the value, f comma value, and now we are going to call it over here. Derivative. Okay. Right. Now in this way, the it will converge. And we need some count of the iterations as well. So we'll take it to be 0 and we are going to increment it every time we iterate. Iterations, right? And then we're going to print what are the number of iterations that it took. And then finally we return the value. So this is the complete optimizer routine that we have. Now we are not going to test them in that main.py file. We are directly writing the unit tests for them because yeah, that would save us some time as well. So let's do that. Okay. All right, so we are going to copy the above part like till here. And we're going to close the rest of it because we don't require it currently. Right, and in the test.py file, we are going to import from the test optimizers. Right, we're going to close everything else. All right, let's start now. Unit testing optimizers. Unit test numpy as np and yeah, from tools.optimizers import. Let's import everything. Okay, now we're going to do this. Yeah, for now, let's just put it test Newton. In the future, we may have different types of optimizers. For now, let's just put it test Newton. And we are going to do test derivative. Right. Now, which function should we take? Let's take okay. Yeah, let's define a function. Or we can, what do we do? Let's define a function over here. D or test function test. Yeah, this would work. And we are going to take an x value. So this is something like the f that we're going to pass in all of that. Or I think, yeah, this would work. Yeah, this will work. So what the function is going to be? Let's think. Let's take it to be a simple polynomial function for now. For instance, we can define not too simple like x square, like a little different, like a little big function. Let's take it to be x plus 1 times x plus 2. That is going to be x square plus 3x plus 2. Right, let's take that. Value is equal to x square plus 3 times x plus 2. Are we correct? Yeah. And then we're going to return the value. Okay, now the derivative is going to be, let's write it over here, 2x plus 3. That's going to be the derivative of it. And we will calculate the derivative at x equals 1. So for that, we are going to have the value 5. T equals 5. Right, now we have the test derivative written over here. Okay. Right, underscore derivative. That's what we're going to do. So we're going to do underscore derivative. We're going to take the self.function test and to pass this. And we are going to pass a value of 1. Right. Then we are going to assert almost equal. First float and second float. So this is going to be value, comma, and d should be 5. Right. I think this is enough. Let's see how the code works and all. Python test.py. So underscore derivative is not defined. Now, okay, are we doing some spelling mistakes or okay? Now this is because the underscore derivative, we just made it a private function in that. So for now, let's just remove this. Okay, there is one more place that we need to do this. It's over here. Okay. Now this field is within light. Now the value is kind of close, but not that close. We need to adjust the precision of the almost equal. Let's see if how we do this. First float places. Right, I think places is the one that we need to adjust, or probably just the next value. Now default is taken to be 7. We are going to take 4 as usual that we have. That is the basic precision that you're working through, right? So the test runs finally. Now we're going to test our Newton method. For that, how are we going to test it now? F, x init, and epsilon. Now, this x squared plus 3x plus 2 currently has 2 roots. So that doesn't make any sense to compute it. Let's just change it for now, so that we have a single root of it. Like if it will converge, then we know what root we are working, or maybe yeah, this can also work. Like it will give us one root of it. We don't know which root yet, but it will give us one root. Let's just print it and see which root we get. Root at the value which will take it to 0. Now we have Newton method over here. Then we are going to give it self dot function test. X init is going to be 0 and epsilon is also going to be 0. So let's just print the value that we have and let's see how many iterations it takes. It's going to be really, really fast. Like, oh, isn't 0 a value? No, 0 is not a root, but it's going to be really, really fast. Let's see how fast. 0, okay, it didn't run. So let's see how did we go wrong. So the problem was here, in this loop, we should have this condition. It should be greater than epsilon to run, not less than. Okay, local variable, right. Since we named this derivative, so we're just going to be naming it f dash. That is going to be simple, like f over f dash. All right, let's run it now. So -1 is one root that we got, and it converged in 7 iterations. Is -1 really a root of this? 1 minus 3, yeah, 1 minus 1 is actually a root. Now let's do some little testing over here. Now x init is actually really close to the -1 root. That's why it converged over that. Let's just go to the right, like 5. Now other root, -1 is one root of this x squared plus 3x plus 2. It's x plus 1 times x plus 2. So -2 is another root that we should get. So let's go towards -5 and then see what value it converges to. It should converge to -2, but we don't know. Yeah, it converges to -2. So we are going like pretty correct in this way. Okay. We can test a variety of functions over here. Let's just name function test 1. Yeah, we can test a variety of functions. That's what we're going to do in this now. The self dot assert almost equal, and we are going to assert that value is equal to -2. And the places we are going to adjust is again 4. Let's see, test is working. Yeah, test is working. Now, since we are on it, we are going to define a little different function that is going to be something exponential function. Let's try that. Yeah, let's see if we can make that. Okay, let's see some complex function, more complex than this polynomial function, and let's see what we get. Okay, let's have the function, very, very complicated function I'm thinking of. Let's take it to be exp, like exponential function e to the power x square plus e to the power x, and we just add a 1 as well. That's 2. Okay, now what the derivative of this is going to be? Let's see. Now the derivative is going to be something, ex square is going to be same, all right, 2x times ex square plus ex, that is going to be same, or we can do something like this, 2x times exp, 2x squared. Okay, and e to the x we are going to type in as like this, and yeah, now at x equals 2, I'm going to calculate derivative. I'm going to see how, using a calculator, I'm going to calculate the value first. Okay, so it's a really big value that is going to be 225.781656232. We're going to write it completely. And now we are going to run this as well. First, we're going to test 1, and then now, yeah, one thing that I didn't note was ex square plus ex plus 1 doesn't actually have a root. So in order to deal with this, we are going to put -1 over here. Yeah, I think now putting a minus over here will just ease the root, because the root is going to be 1 or 1. No, it's going to be something. Okay, let's see. We need a function that has a root as well. So I'll just derive a function for this and then we'll test it. Okay, so we are not going to put a minus over here. Instead, we are going to cut this value and put it towards the end. That way, this function is also going to have a root, actually two roots. It's going to have two roots, something around -0.649 and something around 1.214. Right. Let's see. Now the derivative is going to change. We are going to calculate the derivative again. So now this value is going to be 2.211.0035444034, really big value. Okay, let's test the value now. Let's run the test. Okay, so the value has come out to be 2.0036 actually, instead of 354. So we are going to adjust the epsilon value as well. Let's see how that changes. Okay, so I don't understand why, but taking a slightly larger value than 1e minus 10 actually worked, and this is the result that we get. So not sure why, but yeah, taking a smaller value worked better. Okay, let's write the test for Newton method as well. I'm going to put x in it 0. We're not going to put any x in it at all. Let's just print what value that we get, like what is the root of that. -6. Okay. Okay, so we get -0.64851. So it is similar to the graph that we get on Desmos, like -6. Okay, we can, I think. Okay, -0.649. So I think it's approximately this. Okay, we can increase how much we want to go in. Let's keep going in. This seems to be a really close value. So let's just take it -0.6845. -0.6485. Right, so this now works and it converged in 7 iterations. All right, so it was really cool coding the Newton method in this video. Right, so this is pretty much it for this video. In the next video, we are going to extend the Newton method to vector functions. For that, instead of the derivative, we need to compute the Jacobian of the value of the function that we have. So that is going to be really interesting. And then we are going to move forward with calculating the inverse kinematics. All right, so see you in the next video then. Bye.